Hi, thank you very much for joining us today, and thank you for the introduction. So what is the question that we would like to answer? Most of the metrics to evaluate RAG need an LLM. And what is the best LLM to use with those metrics? Well, we took this business seriously and conducted an experiment that will try to answer this question, or at least give you some more intuitions when you will be choosing your LLM to work with your evaluation. So who are we? We come from Modus Create. It's a consulting company that supports other companies with software development, including generative AI. Twig is the OSPO, remember this abbreviation, of Modus Create. And we are Gen AI research team led by Noor, which is the team is a part of product development practice. What we are seeing here is only a small portion of the team, the one that is focused on the research work. The work that we will be presenting today was done by Joe from the team, Noor, and I. So to answer the question, what is the best evaluator? You know, what is the favorite answer of a consultant? It depends. And that's exactly what we will be showing to you. Stay tuned. So everyone knows by now what is retrieval-augmented generation. So what I want you to take from this picture is like the general diagram that will be showing up later in the presentation. So we have the retrieval step where we have the knowledge base, which is embedded in a vector embeddings. Then we have a generation phase, which is supported by the large language model. And that's basically the system that we are dealing with. So we also wanted to show you how RAG looks in action and explain the OSPO, what OSPO stands for. And OSPO stands for Open Source Program Office that we have in Modus Create. And the RAG in action will show you not only the answer to the question, but also the documents it based the answer on. But, well, why do we have to evaluate RAGs, right? It's, I know that before presentations, they were talking more and more about the importance of reliability. And this is exactly what evaluating is for Gen AI systems. It's like testing for regular software development. We do not want to test on production because our users will be unhappy. For example, they will not call 911, but some other number. And another aspect of that the need of evaluation, is that if you know the Gartner cycle of hype around some technologies, we probably are at the peak of inflated expectations with Gen AI, but we don't know exactly. And what we are trying to do with evaluation and with making sure that the product that we are developing is actually correct is to flatten this cycle. So the technology is more stable and we are not peaking so much and promising things that are impossible. And then we will not go through this delusionment so low. Another aspect of our work is the libraries that can be used for RAG evaluation. So on the top level of this pyramid, you have libraries that propose metrics and implement them, like RAGAS that we will be using throughout the presentation, and TruLens. On the second level, there are evaluation libraries that integrate those metrics into an evaluation product, which is DeepEval and Giscard, as we mentioned. And on the bottom, you have generic libraries that integrate all other tools as well that help you build the whole LLM application, like LangChain and Llama Index. So what are the metrics that we can use for RAG evaluation? Well, we have a system, so we can we can split this system into at least two parts and evaluate each part separately, because that way we can pinpoint the problem more precisely if the problem occurs. So for the retrieval part, the metrics we will be discussing is context precision and context recall. Context precision is a metric that evaluates whether all of the ground truth relevant items present in the context are ranked higher. So yes, there is some connection with the classical precision as well. On the other hand, context recall measures the extent to which the retrieved context aligns with the annotated answer. So the grand truth for us is the answer that you see here. So let's dive a bit into context recall just to see where LLMs are playing their part, because we actually want to evaluate those LLMs that help us with the metrics. So where are they? Just for the intuitions, context recall. So this example is based on RAGAS example, which is super great documentation if you ever come by. So where is the France and what's its capital? And the grand truth answer is France is in Western Europe and its capital is Paris. So the answer one with high context recall has France is in Western Europe, blah, 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 Paris is its capital. So we are all good. But the answer with lower context recall is France is in Western Europe, but we have no mention of Paris anywhere. So the formula for computing context recall is number of grand truth claims that can be attributed to the context compared to number of claims in the grand truth, the total number of claims. So let's see how it works exactly with this statement. First, we have to find statements that we will be comparing to the recalled to the answers. So this is the place where LLM is involved. Oh, what happened? Ah, okay, you can see it here. So this is still good. Okay, we are good. Okay, so this is the place where LLM is involved, and the LLM is used to split the grand truth into statements. First statement, France is the Western Europe, and second statement, France's capital is Paris. The second step is we have to check if the statement is supported by the recalled answer. So for high context, as we see for the first answer, with high context recall, we have this statement, France is in Western Europe, supported for the second one as well. So the first statement is supported by both. And this is also the place where LLM is used. And the second statement, Paris is its capital, it's only supported by the first answer. Okay, so finally we compute that, and it should be quite easy. We recall the context recall definition. And for answer one, we see that both grand truth statements are covered. So the nominator is 2, denominator as well. And for answer 2, the one with the low context recall, only first one is covered. First grand truth statement. So we have 1.5. Okay, that was to show that LLM is involved into computing these metrics. That is why we have to evaluate how this LLM behaves. And the second set of metrics is the metrics for generation part. So in that aspect, we have, for example, answer relevancy and faithfulness. And answer relevancy measures if the generated answer actually answers the question. So the lower score is for answer that is incomplete or contain redundant information, and the higher score is for answer that, as I said, is more relevant. And I wanted just to go through faithfulness for a bit, because it will be interesting in the later part of the presentation. And faithfulness measures factual consistency of the generated answer against the given context. So you see there is some similarity with its context recall, but the main difference is that in here, in faithfulness, the claims are generated from answers and not from the grand truth. So we have context, and from this context we generate answers. And LLM, again, is involved in extracting claims, for example. So what do we do here? We have the metrics, we know the metrics. We know that LLMs are involved in computing them. So what the creatures in the picture are trying to measure RAG, yes, pun intended, and we don't know which one does it correctly, right? So they are different species. And those are our evaluators, our LLMs. And this is us, the GenAI team, who is trying to evaluate the evaluator. And how we do that? By experiment, of course. And how this experiment is set. First, we have to have proper data for the experiment. So for us, data is results of RAG. We do not go into how this RAG is constructed. What's in there is like a very almost off-the-shelf. We have neural bridge data, which we embed into ChromaDB. We have Llama model. The embedding for the ChromaDB is like a very standard one, default. We do not put much thought into fine-tuning those parameters. And the thing that are interesting for us is query, context, and the answer. So those are results from RAG that will be our data for the experiment. And then how the experiment looks like, well, we have different kinds of data. Do I have some pointer? Oh, yes, I have. So we have a query. We have data that comes from RAG, which we will be testing on. And we have the grand truth answer, because that's the data set that we picked, right? So we have grand truth answer and grand truth context. So we know everything that should be there. And for each of the questions from the data set, we compute metric and go further along this data pipeline with it. But we have a data set, so we would like to compute those metrics for all 200 questions that we randomly picked. And then we will be doing some data analysis on that. But what exactly is the input of the experiment? Because the data is something that we work on, but the experiment is with changing LLMs and with changing metrics. That's our input for the experiment. That's what we want to check. And the experiment matrix would look like that. So we have 4 different metrics that we want to check: answer relevancy, faithfulness, context precision, and context recall. And we test 5 different LLMs. So it's Claude, Llama 2, Llama 3, GPT-4, and 3.5. And with that, I give the floor to Nur to show you the results of this experiment.
So is this better or is this better? Same? Okay. In that case, I'll free myself. Okay. So as Maria was saying, we have a not so powerful LLM, Llama 13 billion, that we are using in the RAG system that we have built. Over 200 questions from an open source data set that is used for RAG evaluation, the neural bridge data set. And we are using powerful LLMs here to actually evaluate these RAG metrics. So you can see that we are here using the higher grade. We are using 70 billion, for example, for Llama. We are using Claude 3, Sonnet for Claude, and we are using the more advanced GPT models as well. Okay, so we have actually 2 basic questions that we wanted to answer in this experiment. The first question is whether the metrics values that we are computing are correct. So if I am computing answer relevancy, for example, is it correct or is it not? And even if it's not correct, the second question is, regardless of whether the answer is correct or not, when I run different models as evaluators, do I at least have the same value for these metrics? So do I have at least some faith that whatever LLM I pick, I will get the same result? And I will start by answering this question first because it's easier to answer. So as you recall, we have these 5 models here that you can see, and then we are evaluating on 4 different RAGAS metrics. And you can clearly see that the answer is no, because each model is giving you a different value for each metric. So look here at faithfulness. You have a big, wide gap between the different values for the different models, and the same goes for context precision and context recall, and also to a lower extent for answer relevancy, but it's there nonetheless. And that actually helps us answer the first question about correctness, because if you have a question and 5 different students give you 5 different answers and you know that the answer is 19, you are at least sure that 4 out of these 5 gave you an incorrect answer. So we know that the answers we are getting are not correct, but we have to dig deeper into that. So let's start with the metrics related to retrieval. And I'm talking in this case about context recall and context precision. So you see that in our RAG system, we are getting the context out of the vector database. And in this case, we are getting 5 chunks out of the vector database. Each is about 500 tokens. But we are lucky because we are doing an experiment, so we know what the context should be. And we can compare the context that was retrieved from the vector database to the ground truth context that we know it should have retrieved, and we can compute the overlap between the two, and we know that way what should be the value of the context precision and of the context recall, and we can compare both to what the LLM actually computed. So like Maria previously said, I won't go into the details of the equation, so don't be scared. Just to recall that context recall is how much of my ground truth context I was able to recall in the retrieved context in RAG, and context precision is how much of that retrieved context is actually in my ground truth context. And just to show you quickly how we computed that empirically, so we have our ground truth context, we have 5 different chunks, and we just went over these chunks and checked whether they existed in the ground truth context or not. So in this particular example, we have only 2 chunks that existed in the ground truth context, and we can compute, in that case, both context recall and context precision. I won't go into the details of the computation because I will give you the actual numbers we got over our data set in this slide. So it turns out, this is not too surprising because we had done experiments on recall and precision before without using RAGAS and without using LLMs, and we got similar results. Recall is bad. So in 48, I can see, yes. In 48% of the questions, you actually had 0 chunks in your retrieved context that was relevant to the ground truth context. So you had absolutely no information to go on to answer the question. This is not surprising to us. I don't know if many of you have gone through examples when doing RAG, but it's very common to have that. And when you have 0 chunk in your retrieved context that are relevant to the ground truth context, that means that both context recall and context precision are 0. So in this case, it's very easy to know what these 2 should be. Now for the rest of the questions, which is 52%, we had only 1 relevant chunk out of 5. And in this case, it's also easy to compute context precision is 1/5 or 20%. And we plotted context recall because it's a bit more complicated to compute. But you can see at the right-hand side of the picture that only about 10% of the retrieved context was actually able to cover all the ground truth context. So how can we use this? What we actually did was take this 48%, just 48% of the questions where we knew that context recall and context precision should be 0, and we saw what the LLM value was for the context recall and context precision. So you can see that for context recall, all the LLMs were actually at a level that is close to 0, so that's good, except for Llama 2. For context precision, all the LLMs were also close to 0, equally good, except for the GPT family. We did the same this time for faithfulness. Again, this is a context where you have 0 chunks relevant. And you see a very wide range of values. So we wanted to see why we have that, because if you don't have any relevant context to answer a question, you should think that the faithfulness should be 0, because how could I be faithful to the context if I can't use it to answer a question? It turns out that if you look more closely, so this is an example, I hope I'll be able to pronounce the name correctly. So the question is, who did LeBron James decide to join in the 2010-2011 NBA season? And the answer is, and that's good, I don't know. because the context that was retrieved for this particular question does not have anything to do with this particular player. And in most cases where the context is not relevant, we got an I don't know answer, which is pretty good. This is what you should expect, even with Llama 13 billion. But this is what's happening with the LLM evaluators. Claude is saying, this is a 1 out of 1 answer. This is a great answer because saying I don't know is actually faithful to the context. While as the GPTs and the llamas are giving you a null metric because some of those are giving you, when they are trying to extract metrics from the, sorry, not metrics, claims or statements from this answer, they give you an empty Python list, and others simply refuse to answer because they cannot answer which statements they are supposed to get from an I don't know answer. So we get a null metric in most of the cases. Yeah, so what we've seen so far is that these models are not coherent, they don't give you the same answer, and they are not also correct in most cases. But there's an exception to that, which is the OpenAI models, because if you look here at the average value over the 200 questions for all the metrics, you can see that GPT-4 and GPT 3.5 almost overlap. And if you look at the correlation matrix, so we actually computed the correlation matrix for all of these models over all of the 200 questions for the 4 metrics. And this particular matrix only shows you the heat map for the answer relevancy. But if you look at the correlation, can I show you this? Yes. So if you look at the correlation between GPT-4 and I think GPT 3.5 is here, you can see that it's 99%. So it's almost like saying you can replace GPT 3.5 with, or GPT-4 with GPT 3.5. And at the time, it was also still available to use. It was much cheaper, so it made sense to actually use GPT 3.5 over GPT-4 in cases where the data set was not very specific or was not very domain-centric, was not very technical, because this is the data set that we tested on. I cannot extrapolate for other kinds of data sets. This is not the case for the Llama family of models. So you can see that we have very different average values for Llama 3 and Llama 2. And not only that, but the difference between the metric value for each metric is not the same. And you even have an inversion here where you have Llama 2 has a lower metric than Llama 3, while for all other cases you have the opposite happening. So before I recap the findings of this experiment, I'd like to say 2 words about the challenges we faced. So this null metric problem is actually very frequent. You have it when you have a problem with rate limits. So if you are using OpenAI, for example, imagine you have 200 questions and you have to multiply that by 4 metrics. And if you are changing some parameters of the experiment, you have more as well. We were using LangChain, and LangChain has exponential back off. But even with that, we were running into rate limits. So we had to integrate some wait time in the code so that we didn't run into that, because if you retried 3 times to get the metric from OpenAI and it didn't work, you will get a null answer. And then we also have a lot of empty replies with Llama 3. This is a known problem with Llama 3, but when you have an empty reply, you cannot compute the metric. And finally, you have cases where you cannot extract statements, as I've shown you with the case of I don't know, so you end up with a null metric as well. Another problem or another challenge with the implementation was with RAGAS itself. So RAGAS, if you have used it, you know that it gives you the average value for each metric over the whole data set. And this is not what we wanted. We wanted only, we wanted individual values for each question. So we had to go and use an internal structure. It didn't also preserve the order of the questions, so we had to loop over the questions. To recap, it wasn't a very funny experience with RAGAS. I will just say 1 word about cost. It can add up pretty quickly. So if you are actually including or integrating RAGAS into your CI, make sure that you know how much it will cost you. This is just an example of what faithfulness would have costed us over each of these models. And if you were paying attention, you would have noticed that we did that for only one RAG setting. So we want to do it for multiple and different RAG settings to see if we maintain the same results for these settings. And we also want to compare that to manual or human computed metrics to see how they compare to LLM computed metrics. The takeaway message here is that RAGAS, TruLens, they are powerful because they automate and streamline how you evaluate your RAGs, but you should use them with caution. You will not have correct answers all the time, and we don't know which of these models, based on this data, is the best one. There's no clear winner. You should expect null values, so you should account for that, and you shouldn't expect to have the same values for all LLMs as well. Finally, if you want to dig deeper in this, we will be publishing a technical blog post on our blog. So this is the Twig blog on the first QR code. If you want to read that or read previous posts that we published there, and if you want to rather read case studies or go more on the business side, you can go to the link of our consultancy platform, moduscreate.com. And with that, I thank you. And I'm ready for questions.
If there's any question, I think we have time for maybe 2 questions.
Yes, so thank you very much for the experiment. I kind of have a question on the first example, just for clarification. For on the question, what the capital of Paris or what the capital of France is, because the low context answer, so the low recall answer gave some other claims.
Oh, it was much bit before.
Bit further. Yeah.
This one?
Yes.
Step 3.
Yeah. So the low context recall answer gave a lot of claims that are not in the ground truth, but could actually be true. But I was just wondering if they were actually evaluated. Are they actually evaluated as a claim, or because the main thing we want to have is that where France is, it's in Western Europe and the capital is Paris, right? But there's also there are Mediterranean beaches, right? So that is true, but it's not what we need. It's not relevant, but it is true. Yeah. In the context recall and the context precision metric, do you actually use these claims, or do you just chuck them away?
So you actually extract the claims only from the ground truth answer. In this case, you only have 2 claims here. And then for each of one of those, so you loop over those and you check with the LLM whether they are supported by the context. So you don't look at the other claims.
Okay.
They are not integrated into the equation.
Okay, thank you.
We have time for one last question.
Hi, thank you for the presentation. And my question is about, I don't know if you have integrated that in the experiment, but just a question, if you tried to understand the effect of the hyperparameters in at least for the models that you have access to those.
Okay,
in the experiment.
Yeah. So this is actually part of a slide that I had to gloss over. You are talking about the parameters of the evaluator model, not the model that was used for RAG, right? Because we have 2 LLM models here. We have the LLM model, both. Okay. So we actually wanted to study if you change the temperature for the evaluator model, what will happen? Will you get the same result if you rerun the experiment? And it turns out that even if you change the model, RAGAS will actually overwrite the temperature. So inside the code, if you go and look at how the metric is computed, you have temperature set to 0 so that you have a deterministic output. So how many times you rerun the experiment, you will get the same result. This is the first part of the answer. The second part is whether we tried rerunning with different RAG settings, so with different temperature or different parameters. On the RAG side, we didn't. We only tested one setting. So this is part of the future work to actually have multiple embedding models, multiple chunking models, including re-ranking, for example, tested to see if the results will be maintained or not. Yeah, sure.
Thanks again for the speakers.